Hello, my name is Chris Runyon. I'm a senior engineer at the Salt River Project and work with our Grid Management System Engineering group. And today I am presenting Continuation Power Flow, or CPF, as a voltage security tool for utility applications. The main idea is that CPF is not just a way to create a PV curve. It is a method for turning voltage stability behavior into usable operating information. For example, margin, weak locations, limiting contingencies, and possible control actions. The focus here is on how CPF applies to a vertically integrated utility where generation, transmission, and distribution all affect voltage security. Voltage stability is an integrated utility problem. A voltage issue may begin locally, but the consequences can spread across the system. Generator VAR reserves, transmission transfers, topology, feeder regulators, DER behavior, and load composition can all affect the same voltage security margin. CPF is useful because it gives the different parts of the utility a common language, which is how much operating margin remains before the system reaches a voltage limit. Conventional Newton-Raphson power flow solves isolated operating points. Under normal conditions, this works well because the Jacobian is well conditioned. But as the system approaches the voltage stability limit, the Jacobian becomes ill-conditioned or singular. That means that the solver may fail exactly when engineers need margin information the most. CPF addresses this by adding a loading parameter and tracing the solution path instead of solving only one case at a time. CPF follows the full solution path as system stress increases. The PV curve shows how voltage changes as loading increases, and the nose point represents the maximum loading condition. The voltage stability margin is the difference between the current loading level and the maximum loading level. The key advantage of CPF is that it can switch the continuation parameter from load to voltage near the nose point, which keeps the problem numerically stable. CPF works through a predictor-corrector process. First, the engineer defines the stress path, such as load growth, transfer increase, redispatch, or a contingency case. And then the predictor estimates the next point on the solution curve. The corrector then brings the estimate back onto the actual power flow solution. As the process continues, CPF tracks limits such as the nose point, generator reactive limits, voltage thresholds, and weak buses. A solved power flow case only tells us that one operating point converges. CPF gives more useful information. It tells us how much margin remains, which bus or phase is weakest, which contingency reaches the limit first, and what control actions may help if integrated with a tool like optimal power flow. Those actions may include reactive support, dispatch changes, voltage schedule adjustments, switching, or DER settings. That is why CPF is more actionable than a normal base case solution. The theory explains why a solved case can still be risky. Under heavy loading, multiple load flow solutions can exist, and solutions that are close mathematically may behave very differently from a stability perspective. Bifurcation theory explains the PV curve nose as the point where a stable and unstable equilibrium merge and disappear. Near this point, voltage response can become weak or counterintuitive, so margin and sensitivity become critical. CPF margin is only as credible as the model behind it. Different load models can produce different margins. Constant power loads, voltage-dependent loads, and motor loads may all affect the result. Generator reactive power limits are also critical because ignoring them can make the margin look better than it really is. DER operating modes, inverter VAR settings, and feeder voltage regulation can also change the calculated voltage stability limit. Modern distribution systems are no longer passive equivalents. They are unbalanced, have active voltage control, and increasingly include DERs. Three-phase CPF extends the method to A, B, and C phase voltage states, radial or meshed feeders, and DERs operating in PQ or PV modes. This matters because a positive sequence transmission CPF may miss the actual limiting phase or feeder condition. In the reviewed IEEE 13 bus example, phase C reached the lowest voltage. TX stepping is a related continuation method focused on robust convergence. Classical CPF asks how far the system can be stressed before voltage collapse. TX stepping asks whether the solver can reliably converge to the physical solution for a difficult case. It begins with a simplified, virtually shorted network and gradually restores the actual network. This is valuable because EMS, state estimation, and contingency analysis lose practical value if stressed cases do not converge. CPF fits into a broader utility workflow. It starts with model fidelity, state estimator data, planning cases, load models, and generator reactive limits. Then the utility studies scenarios such as N-1 contingencies, load pockets, transfer paths, and redispatch. CPF produces margin and weak location information, which can then support operating decisions such as VAR support, switching, dispatch, voltage schedules, and DER settings. This value is a common margin language across utility groups. For example, planning, operations planning, within the control room, and within your distribution network. CPF helps answer practical operating questions. How much load or transfer margin remains? Which bus or phase is weakest? Which contingency reduces margin the fastest? Where would reactive support be most effective? Do generator reactive limits or voltage schedules bind? Do DERs, regulators, or tap changers help or hurt? The most useful CPF output is a clear ranking of margin, weak location, limiting condition, and recommended control action. To operationalize CPF, utilities should start by calibrating models using state estimator data, generator reactive capability, and realistic load composition, for example, ZIP models. Next, they should define meaningful stress paths such as load pockets, transfers, redispatch, DER modes, and contingency assumptions. Then CPF studies can be automated across scenarios. The results should be converted into limits, alarms, operator guides, and reactive support priorities. The goal is to move high-value planning studies into operations planning and EMS workflows. So some key takeaways. I guess the main one is that CPF is margin, not just a PV plot. Second, model fidelity determines whether the margin is credible. Third, distribution and DER behavior now matter because they can affect both local feeder voltage and bulk system reactive needs. Fourth, robust solving is essential under stress conditions. And overall, CPF turns voltage stability theory into practical operating information that can support planning, operations planning, EMS studies, and transmission distribution coordination. And this is a mapping to the right of the references and the associated document with this presentation. And would like to thank you for taking the time to listen to this, and I hope you enjoy your day. Thank you very much.